Hey guys, welcome back to my YouTube channel. Today we'll be covering something that we covered kind of briefly in the first video on configuring OSPF. By the way, if you haven't seen that one, check in the description below for a link. But today we'll kind of be starting our conceptual explanation of OSPF with the various stages of OSPF neighbor adjacencies. So in our first video, we talked about, oh, we have these two OSPF routers, but we need to kind of get them talking to each other and exchanging routes. How do we do that? And we went over the configuration steps using network command, using the IP OSPF command under the interface. But we didn't really go into the theoretical overview of OSPF. We didn't go into the conceptual drive. Today, that's what we're going to be doing. We're going to be looking at the various stages that OSPF routers go through when they try to neighbor each other, and the order in which they do that. And at the end, I'll even do a diagram kind of outlining what happens at each OSPF stage, because it can happen really quickly in a real-world environment. Hey guys, this is Calvin after the fact, because just like the idiot I am, I forgot to mention something. So, you can't technically have a custom channel link until you have 100 subscribers on YouTube, by the way. Let's get to 100 subscribers! I don't have a time frame, but let's get to it! Anyway. But I have something better. Even better than this meme, which is hard to do because this meme's hilarious. I have a short link configured on my website, which is blamethe.network. So I have a short link configured for blamethe.network/YouTube. I'm going to put it on the screen so you can go to it. You can use that link, share this awesome channel with 3 videos so far with your friends who are also doing Cisco, hopefully. If they're not doing Cisco, well, shame on them. But yeah, if you want to share this channel with any of your friends, colleagues, whatever, the link will be in the description below, and it will be shown on the screen when I decide to edit it in. Should be right about now. Alright, have fun guys, and enjoy the rest of the video. So, I'd like to direct your attention to this OneNote diagram I have set up over here. I know, super professional, right? Everything messy and yep, lovely, right? So we're going to start on our first stage here, which is down. You usually don't see down, and I'm including it just because it's an LSPF stage. There are 8, by the way, in total. Down, the only one that's not included here is attempt. Attempt is only used when you have static neighbors. So in OSPF, you can define 2 types of neighbors. You can use dynamic neighbors, which is what we did the other day. So we had these 2 routers who didn't know about each other before, and we had them send hello packet to each other, which is OSPF's way of both announcing its presence on the segment and listening for others who are on the segment to dynamically discover them. So we have 2 types of configurations. We can either use that, or we can use the neighbor statement, neighbor, and then a dotted decimal notation number afterwards that denotes what router we're looking for. So router 192.168.1.1, neighbor 192.168.1.1 on the router that's supposed to neighbor with it, right? You never say neighbor and then your own IP address. But what that allows you to do is have an LSPF router actively go after a single neighbor and not just kind of shoot arrows over the place and look for neighbors with hello packets, right? Now, attempt is where I've sent hellos to them, but I haven't gotten anything back. So this diagram is here for dynamic discovery. In fact, I'll add that as a note, dynamic discovery. These stages, a lot of them will apply to static neighbor statements, but it is important to note that static neighbors have that 1 extra stage of attempt at the beginning, right? So down, going back to our discussion here, down just means OSPF isn't even trying. It's kind of like, well, what the hell do you expect me to do? There could be a configuration issue, there could be no IP configuration. You really don't see this one, usually, in a dynamic discovery. The first one that you usually see is Init. Init is basically saying, okay, I've received their hello packet, right? So in dynamic discovery, the only way that you can have a neighbor in the adjacency database, which is the OSPF database that contains, well, your adjacencies, hopefully, obviously. But the init statement basically says, I've received a hello packet, but, and let me see if I can insert, I'm going to act like I've done this before. So this is, let's say this is the OSPF hello packet, right? You got blah, 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 all this other information that isn't really relevant to our discussion. And somewhere in there, there is a section called known OSPF neighbors. I should probably move my face out of the way. I just realized that that's blocking that off. Known OSPF neighbors. And we're going to say something like 10.0.0.1, 10.0.0.2, whatever, right? Whatever the known neighbors are. And the key here is when you receive that OSPF hello packet, right? So you are router 2, I'm router 1. I'm sending a hello packet to you, and you as router 2 are going to be looking for your IP. So let's say this is R1's hello packet. When R2 receives this hello packet, he's going to be looking for, let's say R2 is 192.168.1.1. He's going to be looking, R1 will be looking, or R2, I'm sorry, will be looking for 192.168.1.1 in this known OSPF neighbor section. Because that would indicate that R1 knows about R2. If R1 doesn't know about R2, it's not going to be in here. And in this case, right now, it's not, right? Now, that would cause it to get into init, right? So in init, again, the hello packet has been received, but when the receiving router looks in the sending router's hello packet, it doesn't see its own IP address. So it knows that the other router doesn't know about it yet. And the way that you would get yourself added to this neighbors listing is the same way that you discovered that person in the first place. You are going to send out hello packets to the other router. So in this case, R2 is going to be sending out hello packets to R1. When R1 receives the hello packets, assuming everything's good to go, R1 will add 192.168.1.1. And these updated hello packets will go out, and as soon as R2 receives it, it'll see, oh, well, I'm in here now, so we need to move out of the init stage into the next stage, which is two-way. Two-way means that in this hello packet, I've received an updated hello packet that now contains my IP address. So we are in two-way. And presumably, these routers will move into two-way together. Now, this blue line will be explained later. Moving two-way shouldn't be a stage that you stay in for long. It's usually indicative of a problem if you stay in two-way for a while, unless there is one special case occurring in your network. And we'll go over that special case in a second. It's also why we have this blue line here. But moving on, assuming that everything's fine and you move out of two-way, the next stage is exstart. Exstart, or exchange start, it's not really there for much, but it's super important. Even though it's not there for much, it doesn't do much, but it's super, super important because there's a master-slave relationship established. Now, this isn't the 1800s. We're not going back to slavery. No. In this case, right, the master-slave relationship simply means what sequence numbers are we using. So in the link state packets that are going to be sent in these three stages here, really these two stages, there is going to be a sequence number that's used, and the master is the one that determines those sequence numbers, and they have to line up. So, how you decide the master? Highest router ID. So in exstart, you send these things called database descriptors. And those database descriptors among many other parameters, contains the router ID, and that's how they decide the master-slave relationship. One other thing to know about the exstart state. Exstart stops a lot of different... If you have a problem in your topology, a lot of those problems cause your router's neighbor adjacencies to stop at exstart. Prime example, a super common issue is if you have an MTU mismatch. So let's say I've got a GRE tunnel interface, and one end is set to a different MTU than the other, and you try to establish an OSPF adjacency over that tunnel. Well, what can happen is, even if everything else lines up in Init, two-way, blah blah blah, if it hits exstart and it sees that the MTUs don't line up, because the MTUs are included in those database descriptors, it's going to stop there. It's not going to go on. It's going to keep erroring out. It's going to go down, and then Init, two-way exstart, down, and it two-way exstart. So once that dead timer expires, it goes down, and then it goes through the entire neighbor adjacency process again. It's kind of like a reboot loop with the computer, except now it's happening in OSPF, and it's arguably way more catastrophic. Well, I mean, depending on what the reboot loops do. Anyway, but exstart, again, doesn't really do much. You should be moving through the stage fairly quickly. It is important, though. But this is where we actually start the topology exchange process. So here we continue to have a database descriptor exchange. The database descriptors, by the way, are packets that contain LSA headers. So the point of a database descriptor is, well, to describe a router's LSDB, a link state database, that contains all the OSPF routes that are nodes in the area. Well, it also contains the routes outside the area, but that's a complex discussion into different LSA types I don't want to get into right now. But the point being, the LSDB contains the OSPF routes that router knows about, and it will send the LSA headers, just the important bits, right? Because LSAs can get quite large, but just the important bits that the other neighboring router needs to make sure that the databases are consistent between them get sent. Because here's the thing about OSPF that you have to realize. In an OSPF area, in one OSPF area, all the routers inside it must share the same LSDB. It's why it's so damn hard to filter routes between two routers in the same area, and why it would have to happen from the area border router. Because if you filtered a route out from an update that went to another router in your same area, you've just broken rule of OSPF, because now you have inconsistent link state databases. So the important thing to remember here is this topology exchange process's entire purpose is to get their link state databases lined up, consistent, and then in turn getting them consistent with the rest of the area's link state database. Which is why, again, this sequence number process that we established when we decided a master-slave relationship is so important. Now in the exchange, we have DVDs exchange, which are packets containing LSA headers. Containing LSA headers. And in this exchange mode, you're just sending the database descriptors. Depending on how large your LSDB is, you can be spending significantly longer amounts of time in this stage than some of your other stages. But the point being is that those routers will exchange your databases, and now each router has an idea of what the other router's database looks like. Now we go into the loading stage. The loading stage is where the actual exchange takes place. I know it's kind of counterintuitive, but these are where we have LSRs and LSUs sent out. LSR stands for link state requests, and LSU stands for link state updates. So we have these link state requests sent out where the router basically says, hey, I want this route. So now the routers have an idea of what their router's database looks like, now they are tasked with the job of getting them consistent. So in the loading state, they'll exchange these LSRs, and these LSRs contain, well, requests for routes from the other router. So let's say that between R1 and R2, R2 had, where's my bullet point? 10.0.0.0.1/32. and R1 doesn't have that route. Well, R1's going to send a link state request to router 2 for 10.0.0.1/32. And router 2 will respond with a link state update to R1 for 10.0.0.1/32. So, and I'm going to say that R2 is the host of 10.0.0.1/32. So it's just these routes requesting routes and giving routes to each other is the basic way you can remember the loading state. And this happens bidirectionally between both routers to make sure that they're consistent with each other. And after the loading state, after they have concluded beyond a reasonable doubt that their topology databases are consistent, well, I shouldn't be saying topology database, that's in the IGRP term, their link state databases, are consistent, now we move into the full state, where we have a fully established OSPF adjacency. So, if you've looked at the IGRP LL, which you might not have reasonably so because it's not covered in the new CCNA 203.01, you can see the OSPF has, relatively speaking, compared to EIGRP anyway, a super complex neighbor adjacency process. And it does that just to tick off all the boxes that OSPF has to tick off. OSPF has like an extensive list of parameters that it needs to go through, and even after you hit those parameters, you still have to go through the Topology Exchange process, which is a thorough process in itself. Now, there's one more thing I want to highlight before we go on to the concluding part of our video, which is going to be to diagram this process in some diagramming software. Should be hopefully obvious. Which is, why the hell is this blue line here? So, in order to understand why there's a blue line there, we have to understand, let me get rid of this, actually let me move this out of the way, I'm sorry. We have to understand that there's 3 types of OSPF neighbors. There's the designated router, the backup designated router, DR, BDR, and an other than designated router. DR other. DR other, drother, tomato, tomato. If you say tomato, you're wrong. Now, I pronounce it DR other. Now, when we have these designated routers, these backup designated routers, and these other designated routers, what we're looking at, well, there's various OSPF network types, right? So you can have point-to-point, point-to-multipoint, broadcast, non-broadcast multiple access, right? Those are your main OSPF network types. Now, when we're looking at broadcast segments, as an example, we have DRs and BDRs. The reason why I don't want to get into in this video, but suffice it to say, we do. Now, DRs work in a very special way in terms of OSPF relationships. On a broadcast segment, DR others, let me move this out of the way, DR other adjacencies stop at 2-way. Let me explain what that means. So, and I think to do that, it would be most helpful to have a drawing. I'm going to move this out of the way here. Alright, so let's draw. We're going to have a DR here. I'm drawing with a mouse, so excuse me. And we're going to have O means DR others. Say we have O here. And we'll say we have these links. Now, what OSPF does with this designated router is effectively create a logical hub and spoke. Even if it's not physically wired in that way, it creates a logical hub and spoke. Because where does the topology exchange process start? Well, it starts on the other side of this blue line with the exstart stage. Because in exstart, we determine the master and slave relationship, and then we go on to exchange, where we exchange these database descriptors, and then we go on to the LSAs, LSUs, and then we have a fully established OSPF adjacency, right? But in that in those couple of stages, we are doing topology exchange. Nothing in terms of topology exchange happens here. This is just the prerequisite to make sure that two OSPF routers are eligible to even be neighbors in the first place, let alone do any sort of topology exchange. Well, if your DR other adjacencies stop at the two-way state, what are they not doing? Hopefully you answered topology exchange, or database exchange, sorry, because if they stop at two-way, they're never going to the state. They're never going to exstart. Which means, in turn, they never go to exchange, they never go to loading, and they never go to full. The only adjacencies that ever go to full are adjacencies involving a DR and a BDR. A DR other to a DR other will never go beyond full. But a DR BDR to DR other will, right? And a DR and a BDR relationship will. So any relationship that contains either a DR or BDR is allowed to do topology exchange. Any that don't stop at two-way, and that creates a hub and spoke, because the only routers that ever do topology exchange, the only routers that get their database exchange with, should I say, is a DR. So these DR others, even though they have a physical link, never do topology exchange over them. This just gets stuck at two-way. If you were to try to create an adjacency over that, this would just get stuck at two-way. In turn, you'd have routes flowing up here from this DR other. You'd have routes flowing up here. You'd have routes flowing down. Same thing with this router. Routes flowing up, routes flowing down. But there are never routes flowing between these two DR others. Point to point, you don't have the concept of DR, so this doesn't really apply. But on a broadcast segment, let's say we have a switch. Excuse my artwork, quote-unquote artwork. And these routers, we just create a broadcast segment. The router sends out a broadcast, the switch floods it, right? Basic switching concept. Well, we just create a broadcast segment, so there will be a DR and there will be a BDR. In this case, one of these routers is going to be a DR, one of these routers is going to be a BDR, so it's fine. But if we add a third router, or the fourth router, let's say that this is the DR and this is the BDR. These two routers are DR others. They form two-way with each other, and then in turn, they form full adjacencies to this DR and the BDR, and the DR-BDR handle the propagation of routes to all of the other DR others. So you can see how this quickly becomes a hub and spoke topology, where the spokes, in this case, the DR others, only exchange routes with the hub, and then the hub handles the process of both representing the broadcast segment throughout the area using type 2 LSAs, type 2 network LSAs, and through making sure that all of the other routers, all the other DR others that are not allowed to exchange routes with each other, have the routes from one DR other. So hopefully, again, you can see how this creates this hub and spoke topology, even though they may not be physically wired as such. Now, the concluding part of our demonstration, which is, we have an OSPF domain. I'm gonna move my face down. Alright. Hello. So, we have an OSPF domain. Move this up a little bit. And this is the current stage. Down. Nothing's happening at all. No exchange of anything. And the databases are not fully converged for reasons that I hope are obvious. Init. So now we're in Init. Yay! We're moving up the chain. We have an OSPF hello. Hello. And we have another OSPF hello. Hello. I should change this to a dotted line. Set type to be deleted. Alright. Now I have the solid line. Hello, hello. Now, this is init, even though there's a bidirectional exchange of hellos, because in this hello, in the known OSPF neighbors, R1 is not in it, and in this hello, known OSPF neighbors, R2 is not in it. This is its first hello, so there's no reasonable way, unless R1, we're assuming, by the way, that these hellos came in at the exact same time. If this hello came in first, obviously it would have known OSPF neighbors when R1 sent out its first hello, and that's how it usually happens anyway. But in this case, we're assuming that the hellos are received at the exact same time, faster than CPU processing time, which is hard to achieve. Anyway, so let's say we get successive hellos, and now that they've received each other's hellos, right, assuming everything's fine in the OSPF domain, now they are in it. So again, we're assuming that the hellos are exactly synchronized for the sake of being absolutely ideal. Now that R2 and R1 are in the other router's respective hello messages under the known OSPF neighbor section, we now have two-way knowledge of each other. We have a two-way state, actually. Yeah. So now we're just going to move straight into exstart. So let's assume that this route has a RID of 192.168.1.1. This router has a RID of 192.168.1.2. So this is going to be our master, and this is going to be our slave. Again, this is not the 1800s, you history nerds. Alright, cool, we're in exstart. We've exchanged database descriptors that contain our RIDs, our MTUs, our database descriptors, right? So now R1 knows that it's a slave and to listen to R2's sequence numbers. That's basically all the important stuff that exstart does. Exchange. Now we have the real stuff going on. So we still have DVDs sent, except now the point of the DVDs is looking, or now what the routers do with the DVDs is look into the LSA headers, the juicy parts of the routes, right? And let's make some DVDs real quick. DVD 192.168.1.1/32. DVD R2, 192.168.2.1.32 to 2.32. Alright, so you can see they have nothing in common. But these routers will soon realize that, because in the exchange state, list DVD goes to R1, list DVD goes to R2. Cool. So now these guys have DVDs they can examine. Then DVD, by the way, as a reminder, stands for database descriptors. Anyway, they can see now in the database descriptors, oh, I don't have 192.168.1.1, and I don't have 192.168.1.2. That's router 2. And router 1 can see, oh, I don't have 2.1, and I don't have 2.2. So now that they know that they've finished changing DVDs, and there's a flag that's set in the DVD for routers to know that they're finished exchanging, now they're in loading. In loading, we send these LSRs, link state requests. LSR, link state requests. And then these LSRs from R1, it's going to be requesting, I request 192.168.1.2.1/32 and 192.168.2.2/32. LSR from R2. I request 192.168.1.1/32 and 192.168.1.2/32. Oops, I can't speak today. Again, the point of the loading stage is to make sure that, or the point of the entire database exchange process in general, is to make sure that these databases are consistent. Anyway, so now they've received each other's link state requests, now they can send the full-fledged LSAs in an LSU, link state updates. And by the way, if anyone needs it, LSA means link state advertisements. So in the LSU from R1, here is the full LSA for 192.168.1.1 and 192.168.1.2. You know it's /32. I'm too lazy to type it in. LSU from R2. Here is the, again, full LSA for 192.168.2.1 and 192.168.2.2. So this time, it's not just the LSA headers, it's now the entirety of the LSA and all the juicy bits that it contains. Anyway, now we have these LSU exchanged. They both know that the databases are indeed fully converged, and now they have a full state. So hopefully you can see how these routers go through the topology exchange process from a super high level. This is going to be concluding our video on a high-level overview of OSPF neighbor adjacencies. I hope you enjoyed it. I hope you took something out of it. Let me know in the comments down below if you have any questions, any feedback about this video style. I'm trying to constantly improve the quality of the videos. And yeah, hopefully you guys learned something. Go do more Cisco or more Microsoft, because Microsoft's fun too. Anyway, have fun, guys. Yeet!